Hello, I'm Jae Park from Seoul National University, South Korea. First of all, thank you very much for inviting me to this ICCAS 2021. It is my great honor to have this opportunity to give a talk today. The title of the talk today is Control Issues on Bipedal Walking Robots. So Honda Asimo from Japan, Atlas robot from Boston Dynamics are popular and very famous walking robots. If you look at this Honda robot Ashimo, it can run, hopping, and walking around in human environment and do the manipulation. And it has many advanced features, not even walking. And if you look at the Boston Dynamics, it is really impressive. The walking is much like natural, and now it has very powerful motions and dynamic motions. And not even these two robots, but there are many bipedal humanoid robots. So these are 13 examples of the robots, but there are many more. So today, what I want to explain and discuss is the main characteristics of bipedal robots compared to the conventional manipulators, fixed-based manipulators, and the control issues associated with them. So these are the three kind of the main characteristics that I listed. Probably there are more, but I want to emphasize on these issues. And because of them, we will have the issues in hardware control and planning, and many more probably, but mostly focused on control I would like to discuss today and in relationship with the others. So very first one is moving base. Basically, the robot itself is moving, unlike fixed base manipulators. So if you think about fixed base manipulators, the weight of the manipulator matters, but it does not matter that much compared to bipedal walking robots. So especially for fixed-based manipulators, the weight of the base can be actually quite heavy, and sometimes it can help to stabilize the whole manipulation of the robot, especially when we have dynamic motion. However, if you think about two-leg walking robots, so robot has to move around. That means the robot has to be a little bit lighter. Otherwise, if it is heavy, then we will have more powerful actuators to support this heavy robot. That means we will have a heavier motor for stronger force. That means the robot becomes more heavier and it can get worse. So it's better to have a better cycle, to positive cycle basically, that robot has to be much lighter. That means we will have to think about what to use as actuators, electronics, computers, and sensors and batteries. There are all these hardware components has to be considered seriously to make the robot lighter. So it will require basically different designs of hardware. And another interesting issue is that because the robot is moving around in the environment, so where it is also important, and it has to be measured with respect to the environment, so that we can plan the locomotion. So there we need an issue of sensing and localization. Today I will probably discuss more about the design aspect of hardware and control issues with it. So very first one is the leg design, and the bipedal walking robot doesn't have to be really similar to human leg, of course. However, human leg is one of the very good example because we can walk around very well. And if we think about bipedal, we will have two legs. And sometimes we want to stand still even on one foot. That means we really need a foot. If we don't have a foot, that means if it is a point foot, it is very, very difficult to have stand still motion. Basically, we really need to move around to balance on one point foot. However, if we have a finite size of foot, then we can stand still and do some manipulation if it is needed. And especially when we have 2 feet, then it can be more stable. So that's why we will need a foot in many cases, and that means ankle is very critical because the ankle joint has to support the whole body of the robot in some cases. So the strength of the ankle is critical. Sometimes we don't want to make it really strong. That means it can be a little bit compliant. Then it can create some control issues. And also the hip joint is quite similar. And in terms of the degree of freedom, human leg, one leg probably have 7 degree of freedom at least. And for humanoid robot, the minimum number of joints could be 6. Maybe a little bit less than 6 can be okay, but we will have limitation in motion. So many of the humanoid robot or 2-leg robot have 6 DOF for each leg, and this is the main feature of the robot leg design. And as I mentioned, ankle joint has to be quite strong, and hip joint also has similar feature. So strong actuator or appropriate actuator is essential. And the actuator decision can affect the robot design a lot. And there are probably many choices, but popular ones are hydraulic actuators and electrical motors. And there are pros and cons, but roughly speaking, hydraulic actuators are typically stronger, but have some issues with the response and efficiency sometimes. And typically, it's a little bit more difficult to design. And electrical motors are known to be quite fast, and efficiency is very good, but many cases, the force or power is a little bit weaker compared to other actuators. So depending on where in bipedal walking robot or with the right technology at the period of the development, you can choose different actuators for different purposes. So in historical aspect, bipedal walking robot has been developed really as an early stage 1960s. And 1960s, 70s, and 80s, when I investigated, hydraulic actuators were more popular. And probably because at the time, hydraulic actuators were more suitable for supporting the leg designs, I believe. And later on, in the 90s and 2000s, electrical motors became more popular instead of hydraulic actuators. And in 2010s, we have a little bit more variations from electrical motors, and also hydraulic actuators were also used and have been used so far. So this is kind of the trend. I think it is really in relation with the development of the technology for hydraulic actuators and electrical motors, and also associated gears technologies, so harmonic gears and planetary gears, and also the motor driver technologies. So at the period of the development of the robot, there were probably many choices, but these choices were depending on the technology, appropriate technology for the design. And these were a kind of trend. And as I mentioned, in the 2000s, electrical motor with harmonic gear were quite popular. And in that period, BLDC motors were started to be used with harmonic gears, and the efficiency was increased by that. And all of these robots were designed with a very similar kinematic structure with similar actuators. And later on, quite recently, in the 2010s, many people have been interested in compliant actuators. So what that means is that we want to make compliant actuators at the joint level. So before, when we use electrical motor with gear, typically it was quite rigidly controlled on all these joints, especially with the position. So we command the position on each joint, and then electrical motor with gears were tightly controlled to follow the trajectory of the motors. Recently, in the 2010s, what people have been interested in is building compliant actuator at the joint. So when we have impact from the ground while walking, we want to observe or deal with at the actuator level, at the joint level. So hydraulic actuators have been investigated in this aspect, and electrical actuators will also have been investigated in this aspect. So we sometimes attach torque sensor to monitor the torque at the motor, or we put spring component to be a little bit more elastic. And sometimes we use roll reduction gear ratio so that it can have backdrive ability. So there are many variations to have these compliant characteristics. And another important characteristic is the impact with the ground, basically. So when two-legged robot walking around, it's not only moving around, it has to have contact with the ground to move around with a leg, right? It's a little bit different from the wheels. So whenever we are having contact with the ground, because of the weight of the robot, we will have constant impact, right? And these impacts can be really critical for the robot, because if we don't deal with it very well, then we may lose balance, that means falling, or sometimes we damage actuators. So it is related with the hardware and control both. So main approach at the early stage, especially in the 1990s and in the 2000s, we used position controlled robot. That means we are commanding position to the robot, and then all these motor drivers are trying to tightly control these motors to follow trajectory of the commands, especially with electrical gears and electrical motors and harmonic gears. And to do that, we attach force torque sensor on the foot, and then we measure the impact force. And depending on that, we adjust the leg motion to observe the impact and stability. However, later on, from 2000s and 2010s, people have been developing compliant actuator techniques to accommodate joint torque control. So what that means is, as I mentioned before, whenever we have impact, we try to do something at the joint level. And this is related with the hardware design, as I mentioned earlier. So when we control the joint torque and we also command the joint torque, it can be more compliant with respect to sudden changes of the environment and disturbances. So in the 2000s, with the hardware of electrical motor plus harmonic gears, impedance control based upon position control have been popular. And this has a very great performance. And even so far now, I think this is one of the best technologies that we can use for two-leg robot, for robust walking. And this performance is great. And in the 2010s, as I mentioned, people have been looking at more possibilities for compliant actuators to accommodate or to develop torque control approaches. And these approaches are getting also popular, although there are still limitations because we are not there with the hardware yet. And also controllers have to come with the hardwares. So we are developing the hardware and controller and back and forth and going in very good direction these days. So there are many different actuators and control approaches these days for various robots. So you can see here various types of two-leg robots with the different combinations of the actuators. The final main characteristic of two-leg robots is already mentioned, that the robot has many actuators. So as I mentioned, one leg usually has at least 6 DOF, 6 joints, and two leg means 12 joints. And when we have upper body, like a humanoid robot, then we have many DOF. Then how can we plan this motion, especially with respect to environment? Sometimes we have to interact with the environment with the legs or sometimes with the upper body. So motion planning is quite difficult. And this is an example of the robot in our lab, Dokkabi, and Dokkabi in Korean. It has 33 degrees freedom with the joints on the waist and the neck for the head. And planning for this humanoid is quite complicated. If you think about path planning in space, and that's also quite complicated in 3D space, and motion planning should be done in 33 degree freedom, and you have to plan footsteps, and if there's obstacle and uneven terrain, this is quite complicated. And also we have to account for all the constraints in addition to the degree freedom. So we will have joint limit, self-collision, and torque limit, and contact on the ground. So accounting for all these constraints, we have to plan at many different levels. So this is quite difficult issues. So if you think about locomotion, from one place to the other, we want to move. And there are so many possibilities. What's the optimal solution for our robot? So this is a great question. And if you account for whole body motion of the humanoid, which is 33 degree freedom, moving one place to the other, it will take a lot of time. So people have different approaches, especially with the simpler model, so different levels of planning. So one very popular model to plan locomotion is inverted pendulum model. And inverted pendulum model is nonlinear, unfortunately. So we simplify further to be linear, so we call it linear inverted pendulum model. And this is the relationship between zero moment point on the foot and the COM. So this simplified model describes this, assuming that the height of the COM is constant. And at the early stage, analytical methods have been developed to plan COM given footsteps. However, this was quite a good approach because it's a linear equation and we can solve it analytically. However, it was not easy to do it online. So why do we need it online? Because we may want to change motion of the COM during walking, or if there's a disturbance on the foot, or if there's an obstacle, we have to avoid the obstacle and react to the disturbance. So to do that, later on, optimization-based approach has been developed. And one of the most famous one is preview control. And recently, model predictive controls are getting popular. And now with a little bit more computation time, but still it's doable because we are using simplified model of LIPM, linear inverted pendulum model. So now we can deal with sudden disturbances and online replanning is possible. And this is one example. With MPC, we plan online COM motion and deal with this kind of uneven terrains. And another approach is using whole body motion to balance. And here we again use optimization method to deal with angular momentum control. And this is the Atlas robot from IHMC. You can see this great balancing motion using optimization method. So far, I have been discussing all these three issues, and it was quite brief. So I hope I explained okay in very short time. So I tried to explain these features with an issue, mainly with control, but hardware and planning. Now, what's the future direction in two-leg locomotion? Two-leg locomotion has been developed very well, and of course there are still many problems that I have mentioned, but another direction that we are pushing is whole body locomotion. So while we move around, walking around, we also want to use a whole body. So this is very important because we can use now upper body motion to help lower body motion or locomotion, and also we can have very dynamic behaviors. So this is really, really impressive video from Boston Dynamics, Atlas robot. They don't publish many papers, so it's a little bit difficult to understand what's going on in detail. However, they explain sometimes in the workshop and magazines. So from those information, this is what I've summarized. So what they do is in offline. So they create a library of template behaviors with mainly trajectory optimizations. Sometimes they use motion capture data and then use again optimization to create a library of template behaviors. Then in online and actual execution time, use perception, and then create sequence of motions from the library, and those will be the reference trajectory of the robot. And if we execute this reference trajectory of the motion to the robot, then robot will slow down, of course. So we need feedback, right? So to do that, they also again use optimization approach, model predictive control. And to make balance, they also use force torque sensors on the foot and probably other sensors too, like IMU, and use model predictive control to follow their reference trajectories. So what they have explained is they are currently using optimization-based more than others, and especially they are looking at the learning technologies, but in these videos, they were not applied that much. That's what they have explained. So, of course, another direction of the leg locomotion must be learning. And these are another very impressive video from Agility Robotics, recently released. So what they do is kind of reinforcement learning. So to do that, what they do is they identify the model, their robot's model, as accurately as possible. And then in the training, and their training is done in simulation. So they are using sim-to-real technology. So they randomize the robot model a little bit so that it can be robust with respect to the robot itself, because when they make a robot, the model parameters can change. And also to deal with many different terrains, they randomize the terrain information in the simulation. And also, they are using estimated state, not absolute state in simulation, so that it can be quite similar to the real situation. So this is the training offline in simulation. And what do they learn? So their basic trajectory is, again, from simplified model, slip model. Slip model is another different form of inverted pendulum. So slip means spring-loaded inverted pendulum model. And then they try to compute the deviation from this model. Then in online, so in actual deployment, so they again create this reference trajectory from slip model, and the deviation is computed from the learned controller from simulation. And this was quite successful in their implementation. So I think these two are quite important research direction in two-leg locomotion. At DIROS, what is DIROS? Dynamic Robotic Systems Laboratory, which is the name of my lab, my research group. So in our lab, we are trying to work on some of the aspects of two-leg robot walking. So we cannot like deal with all these topics. So we are now focusing on three topics out of many. And the very first one is real-time whole body motion creation. So when we walk around, we want to create a whole body motion, of course, with the walking together in real time, so that we can reactively create a motion. And we also want to work on compliant motion control technology. So this is not a new topic, but for us, we want to use very limited sensors, especially only with the intrinsic sensors. So we want to minimize the use of external sensors such as force torque sensors on the foot, because when we have constant contact, we have an issue with the hardware, so it can break down. Or force torque sensors is, if you have any experience with it, it's quite difficult to use in terms of the calibration and bias and things. So I think it will be more robust without them, or minimum use of them. So this is another research direction that we are taking. And we have been building our own humanoid robot, and this robot has different characteristics from others. So we want to identify what those are and then solve the problem for ourselves. So these are three research directions in our lab for two-leg locomotion. And this video was presented last year, ICCAS 2020. And here you can see this upper body or whole body motion with walking, and these motion were generated online. So we can change the stride length or step time, and these were done with the QP controller, which is optimization-based controller. And planning also was done with the optimization approach. And this is another research direction that I have mentioned. So if you look at this video, we have compliant motion. So when we put something on the feet abruptly, we will have external force on the robot, which was not expected. And DOB means disturbance observer. So this disturbance observer estimated without actually force torque sensors on the feet, and use the information to make it compliant on the joint level. So this is our approach, and this was quite successful and robust, even for external force on the upper body. And quite recently, what we have worked on is collision detection, and almost like to estimate the contact force when we have an impact on the manipulator. So this is an example with the 2DOF robot, and this was verified on this robot, and the result was quite interesting, that our estimate contact force and timing were quite comparable, even with joint torque sensors. So we hope that this technology can be used for walking later on. And another direction is to identify our own robot's hardware characteristic and utilize them for our controller. So we have harmonic gears in our robot, and we found that our selections of the motor and gears were having quite compliant characteristics, which was not expected when we built it. So now we are identifying this compliance and utilize the dynamics behind it, so that we can account for this flexibility in control. So our goal is to have joint torque control with the motor current information, and using this additional dynamics characters to make it quite accurate position control. So basically what we want to do is compliant motion with the electrical motor and gear system without external force torque sensor, while we can still maintain high position performance accuracy. And with all this development of two-leg robot, and if it is combined with manipulation, I believe that there are many possibilities and many applications can be done in the future. So in the video, this is one example that I can think about. So teleoperated mobile robot for industry. So in the factory, I think this robot can help human, or instead of human, it can do quite difficult work or dangerous work. So this is one application. Of course, mobile robot can be applied instead of the legs, but I think two-leg robot can have a room, or can have advantages in some cases. And other applications can be hazardous environment or disaster area, or logistics is very important in these days, especially with the corona situation. And service robot is also very needed. So we will have many possibilities. And in the final slide, I would like to show our very recent development. So we are now participating XPRIZE avatar robot competition. And we have created quite interesting video based on charade. So you can see the robot motion. As you can see, avatar robot means that there is no operator, and the avatar robot will be an avatar of this operator, right? So the operator will feel like the he or she is there in a remote environment. So here you can see that my students are playing with the operator through the avatar robot, the Python charades.
질문이 있습니다.
네, 김동현 씨.
주제가 무엇이죠?
네, 오늘의 주제는 운동과 관련된 단어입니다.
So subject of
게임에 앞서
the Python charades today is the
자리를
sport.
정하겠습니다.
So I'd like to show a bit of walking because the topic of the talk today is walking. Here
네, 여러분 주의해야 할 점은
we can walk around and you can see the foot interface in the left lower corner. And he starts to explain about baseball. So the answer is baseball. And Youngjae, my student, called avatar robot. And now he's going to explain what it was without saying anything, right? So as it on charade, he or she has to use only motion to explain the answer. So he explained baseball, and operator understood, right? Okay. And then he turned around and explains to Uno, this is baseball. And he got the correct answer.
정답.
네, 정답.
야구?
네, 정답입니다.
And everybody is happy. Right? So this is not a serious application, but I think this shows very interesting possibility of using humanoid robot as an avatar robot system. And I really like this video because whenever I see it, it's quite fun, in my opinion. And it's very exciting. And the robot is moving around and act like a human within human environment. So with this, I would like to end my talk. And thank you very much for listening my talk today. And if you are interested in more work in our lab, you can visit Dairos snuac.kr or YouTube channel. Thank you very much. Bye.